In this video, we'll talk about the probability that an event A occurs and then an event B occurs. And we'll find this probability using something called the multiplication rule. So let's start with an example. Suppose there's a two-question quiz with a true-false question and a multiple-choice question, and that multiple-choice question has four possible answers. We could call them A, B, C, and D. So if you're purely guessing, what is the probability that you'll get the true-false question right? If you're purely guessing, what is the probability that you'll get the multiple-choice question right? And if you're purely guessing, what is the probability that you'll get both questions correct? So try those out and we'll talk about them together. Okay, so the probability that true-false question is correct, we could call that probability of t, is 0.5 or 1/2. The probability that the multiple choice question is correct, so the multiple choice question, there's four possible answers. If you're purely guessing, it's 1 out of 4. We're assuming only 1 out of the 4 is correct, so 0.25. And what is the probability that you'll get both questions correct? So one way we could think about this is to think of it as a tree diagram. So we could think of it first as we have a true or false, and those are two possible answers you could give the true-false question. Then for the second question, if it's A, B, C, and D, there are four possible answers you could give. If there's A, B, C, D, then there's four possible answers for that as well. So if we think about the sample space for this problem, then our sample space is true A, true B, true C, true D, false A, false B, false C, and false D. So there are 8 elements in the sample space, and we assume that only one element is correct. So only one sequence of answers is correct. So maybe let's just suppose that it's false and C. So that means that the probability that both the true-false question is correct and the multiple-choice question is correct is 1 out of 8. That out of all the possible answers you could give, we're assuming that just one of them, in this case false and C, just as something to pick, that happens to be the correct sequence of answers. There's only one such correct sequence of answers out of 8 possible answers in the sample space. So 1 out of 8. So something to notice in this particular example, that the probability that the true-false question was correct and the multiple-choice question was correct was 1/8, and that also happens to be equal to 1/2 times 1/4. Remember, when we multiply fractions, we multiply across the numerator, multiply across the denominator, so 1/2 times 1/4 is equal to 1/8, and that's equal to the probability that we get the true-false question correct times the probability that we get the multiple-choice question correct. So the probability in this case, in other words, does this always work? Is it always true that the probability that A occurs and then B occurs is equal to the probability that A occurs times the probability that B occurs? Does that always work? So to think about whether or not this sort of multiplication rule always works, let's think about the following example. So there are 8 marbles in a jar. 3 are green and 5 are blue. What is the probability of taking a green marble from the jar and then taking a blue marble from the jar without replacement? So in other words, if we've got these 8 marbles in a jar, we're picking them randomly without looking at them. What's the probability that we first take out a green marble and then set it aside and then take out a blue marble? So think about that for a moment, and we'll talk about that too. Okay, so with our 8 marbles in the jar, what's the probability the first is green and the second is blue if we don't replace the first marble after drawing it? So probability of green and then blue would be equal to, in this case, well, 3 of the marbles out of 8 are green. And then the next marble that we take out, there are 5 blue marbles, but there are just 7 marbles remaining in the jar. So it's 5 out of 7 instead of 5 out of 8 for that second marble. So this is pretty close to what we were doing before. So this is certainly the probability that the first marble is green times the probability that the second marble is blue. But it's not just the probability the second marble is blue, like without thinking about the first marble at all. This is given that the first marble is green. So this is like a horizontal bar, and this is red, probability of green given blue. So we'll see this more generally of blue given green, the probability that the second marble is blue given that the first marble was green. And in general, this is called the multiplication rule. So the multiplication rule is that the probability that A occurs and then B occurs is equal to the probability that A occurs times the probability that B occurs, where probability of B given A, probability of B vertical slash A is read as the probability of B given A and means the probability of B occurring given that, or assuming that, A has already happened. So in some cases, we need to adjust the probability of the second event to reflect the fact that of how the first event occurred. To just think about this a little bit more, let's think about this example. So for the jar with 3 green and 5 blue marbles, what is the probability of first getting 2 green marbles in a row without replacement, then getting 4 blue marbles in a row without replacement, and finally 4 green marbles in a row without replacement? So think about those just for a moment. Okay, so 2 green marbles in a row. So this is the probability that the first is green and the second is green. And so that's equal to the probability the first is green times the probability that the second is green, given that the first was also green. So this is 3 out of 8 times, now there's only 2 green marbles remaining out of 7 marbles remaining in the jar. So 3 out of 8 times 2 out of 7. And so we've got 6 out of 56. How about 4 blue marbles in a row? So this is the probability of blue and blue and blue and blue. And so this is the probability the first marble is blue, that's 5 out of 8, times the probability the second marble is blue, given that the first was as well. So now there are 4 blue marbles remaining out of 7 total marbles in the jar, times 3 out of 6, times 2 out of 5. And again, when we multiply fractions, we're just multiplying across the top and across the bottom. We can notice the 5 and the 5 cancel out, so we can get rid of those. This 2 and 3 cancel with our 6. And so we're left with 4 out of 7 times 8, that's 48. 56, sorry. So 4 out of 56 would be our final probability for that. And what's the probability of 4 green marbles in a row without replacement? So probability of green and green and green and green. So that would be 3 out of 8 times 2 out of 7 times 1 out of 6 times 0 out of 5. There would be no more green marbles to choose from. And so that's a probability of 0. That is impossible. There weren't 4 green marbles to choose from, so we could go through this, or we could automatically recognize that that probability is 0. All right, let's take a look at another example. Suppose there's an egg carton with 9 good eggs and 3 bad eggs. Suppose that we take out 2 eggs one at a time, crack them, and either label them G for good or B for bad. So what is the probability that one of the eggs was good and the other was bad in either order? One thing to notice here is that because of this either order, we're really looking for the probability of a good egg and then a bad egg, or a bad egg and then a good egg. So that's what we're looking for. So think about how you might use both the addition rule and the multiplication rule in this case, and we'll talk about that in just a moment. Okay, so we're looking for the probability that the first egg is good and the second egg is bad, or the first egg is bad and the second egg is good. And these are different events, just like with our heads and tails, how we needed to think of a tail and a head as a different simple event than a head and a tail, and that was important so that our probabilities were accurate. We need to think of these as separate events as well. So what is the probability of this? First of all, thinking about OR, remember that OR goes with addition. So this is equal to the probability that the first egg is good and the second egg is bad, or so plus the probability that the first egg is bad and the second egg is good. And theoretically, we have to subtract off the probability that both of those events happen simultaneously. But we're just taking out 2 eggs, so it's not possible that the first egg is good and the first egg is bad at the same time. So these 2 events are disjoint or mutually exclusive events, and because they are mutually exclusive events, we don't have to worry about the probability of both of them simultaneously occurring. So we just need to think about each of those probabilities. So this is equal to the probability that the first egg is good times the probability that the second egg is bad, given that the first egg we already took out was good, plus the probability that the first egg is bad times the probability that the second egg is good, given that the first egg was bad. And so this is equal to, there were 9 good eggs out of our 12 eggs altogether, times there were 3 bad eggs out of the 11 eggs that we had in there remaining after we've cracked the first egg, plus the probability that the first egg is bad, 3 out of 12 times 9 out of 11, 9 good eggs remaining out of the 11 eggs in the egg carton. And so we just have to calculate what that is equal to. So we could do a little bit of cancellation. 3 out of 12 is the same as 1 out of 4, just canceling. Similarly, we could cancel here. And so this is 9/4 times 1 out of 11 plus 1/4 times 9 out of 11. That is 9 over 44, 2 of them, so times 2. So that's 9 out of 22. So that is our final probability of that event.